Hello, good morning, good afternoon, good evening, wherever you are. We thank you so much for joining today's webinar. I'm Naomi Gillia with Bloom Energy, and I'll be your host for today's session. Again, we welcome all of you, and we know you have busy schedules, so we appreciate you joining us today. Now, before I turn it over to today's presenter, I'd like to open up the webinar with a polling question. And so around your greatest power challenge. So if everyone takes an opportunity to answer, what is the single greatest power-related challenge your organization is facing with data center expansion? Is it speed, long delays for utility grid connections? Is it reliability, ensuring uptime and avoiding grid instability? Is it cost, high and unpredictable electricity prices? Is it sustainability, meeting decarbonization targets and environmental regulations? Or is it scalability, securing enough power for massive AI-driven builds? So I'll give everyone just a few seconds to respond. All right, lovely. We'll go ahead and close the poll and love to see if there's any results. All right, so wow, a good many of you have shared that speed is one of your greatest power challenges. And so it's great information followed by reliability and cost. And so thank you so much for taking that time to share the results there. And I will now turn it over to Akhil Bathija, who will be going over today's content.
Thanks, Naomi. Hi, everyone. My name is Akhil Bathija. I'm the Director of Technology Strategy here at Bloom Energy. I've been with Bloom for about 9 years now and got to wear a number of different hats across my journey here. Started my career helping us expand internationally, spent some time doing sales in the U.S., working with data center as well as C&I customers, spent some time in product management, also led our business development efforts around the hydrogen electrolyzer. And most recently, I work as part of our technology group, helping defining our technology strategy to ensure that we meet the needs of our customers today as well as going forward. Really excited to spend some time over my time here at Bloom. I've got to interact with folks in the data center space throughout my time, and it's been a great learning experience for me. I've learned a lot about the opportunities and challenges that the industry goes through. Really excited to spend some time today talking a little bit about fuel cells, how they work, and talking about a little bit how we can help address some of those opportunities and challenges. Before we dive in, I just want to point out the cover slide that I chose to use today. And this is an installation in Korea that's in the tens of megawatts. And I just want to show a couple of things. Like one, the technology is inherently scalable. You can see how we're using that same Lego block over and over again to hit like a relatively large size, as well as like the tower that's being built in the background that also holds the fuel cells, as well as it's somewhat picturesque and they're really aesthetically pleasing. With that, let's jump right in. So since this is a 101, I thought I'd start with some basic facts about fuel cells. First and foremost, the thing I want to make sure we all understand is we are a form of on-site power generation that produces primary power. What does that mean? That means that we install these assets on our customers' premises. They're right there, right adjacent to the load, producing power. When I say primary power, what I mean is we are not a backup solution. We are always producing power for our customers to avail of. This allows our customers to take advantage of reliability and various other attributes and always draw from that power that's banked there available for them. We also produce power uninterrupted. Those in the data center space are well familiar with a device called a UPS, the uninterruptible power supply. It's responsible for producing a very pure waveform and a very high quality of power. We use those sort of inverters in our devices to produce that pure sine wave of high quality power. We also run on pipeline natural gas. I know a lot of people, when they hear fuel cell, think about hydrogen, and we certainly can run on hydrogen. But today, a vast majority of our installations run on affordable, available natural gas that's delivered via pipeline across the United States and all over the world. We're an ultra-reliable solution. Data centers trust us to stay on and keep their facilities running. And we were often measured and designed to hit metrics of reliability. We can go up to and beyond 5 nines through easy configuration of our system. We also produce this power without combustion, and that results in near zero air pollution. That's near zero NOx, near zero SOx, and near zero particulate matter. Our solution's inherently scalable. If you look to the right, I've got a picture of another site that's in the tens of megawatts, and you can see that they just copy pasting the same block over and over and over again. We're now configuring these devices into sites that go into hundreds of megawatts and beyond. Finally, and most importantly, we're price competitive versus other solutions. At my time at Bloom over the last 9 years, that's not always been the case, but we've been on an aggressive cost reduction trajectory. Double-digit percent reduction year on year consistently through the time. And now, as we're going to see later on in this presentation, that allows us to provide these data centers with really compelling economics. So with that, I often hear a whole bunch of myths that hopefully I'm going to address some of, and I've addressed some of them, that they're not ready, that, we always get confused with batteries, and that's why I made it a point that we're an on-site form of power generation, running on hydrogen, which we can, but not always. The one that I think is most interesting is the last one. If they're so good, why aren't people using them? And to that, I respond, they very much are. Bloom today has over a gigawatt and a half deployed across 1,200 sites all over the world. Let me draw your attention to the left, where we talk a little bit more about our data centers. So, about this time last year, we signed a deal that was up to a gigawatt of power for AEP, American Electric Power. AEP is the US's larger owner of transmission distribution assets, and they saw incredible demand from their data center customers that was challenging for them to meet with their existing infrastructure. So they've invested, they've decided to help their customers realize the benefits through deploying Bloom Power. And you can see AWS and Cologix as projects that have been announced on that partnership. Aside from that, we have over 400 megawatts in data centers installed and running today, and some important names over there. In fact, Equinix, which is one of the logos you see down there, it's been in public domain that we have over 100 megawatts deployed with Equinix alone. Just a few weeks ago, we announced a landmark deal with Oracle, and more data centers are realizing our value. On the right, I've got some of the other industries that use us as well. And all of these industries, data centers included, use us for really four reasons. And there's four pillars of value creation. First and foremost, it's time to power. We saw in the poll at the start of this discussion, that is the top of mind topic for the audience today, and that's something that is top of mind for all of our customers. More and more businesses are growing. Data centers need to install and deploy these GPU chips that they've bought at great expense. There's a little bit of a race going on training the models faster than your competitor, and that requires getting power today. Unfortunately, the grid infrastructure and traditional assets are not able to meet that. We're able to deliver tens to significant megawatts to our customers in months, not years. And that enables business growth. That's not only for data centers, but also manufacturing. It's also for other industries too, who are quickly trying to grow and expand. Second lever of the value proposition reason customers buy is the reliability. We talked about how it can be configured to 5 nines and beyond, and we're gonna dive a little deeper into that and how that works and the technical reasons behind that through this presentation. But that's a compelling reason for customers to buy. If not a data center, a hospital can't afford to lose power during an operation. A manufacturing facility is investing significant amount of money in their equipment and do not want to have any downtime. Third part of the value proposition is the sustainability. So I talked a little bit how we're non-combustion and we have near zero air criteria pollutants. We're also extremely efficient even when running on natural gas. That means by we consume less natural gas than other forms of energy generation, and that leads to less CO2 emitted. That value proposition expands even onto water and noise and other parts of the sustainability. Um, Finally, it's cost competitiveness. For a lot of these customers, energy spends a significant portion of OpEx, and any savings can be meaningful for their shareholders and various stakeholders. So let's jump a little bit on how a fuel cell works. I'm going to draw your attention to the top of the slide here, where I've got the side profile view of an individual cell. So I'm going to age myself a little bit with this reference, but when you look on the cell top on, it's roughly the size of a floppy disk. We make these cells and we take the electrolyte and we print on the anode and cathode. It takes in oxygen from the air around us that gets ionized as an oxygen ion gets passed on the anode, where it reacts with the natural gas. It's an electrochemical non-combustion reaction that produces electricity. So a couple of salient points I want to note on this reaction. Like I said, it's electrochemical without combustion, and that means there's near zero NOx, SOx, and particulate matter. Additionally, there's no moving parts in this core part of our power generation. That's very important from reliability and resiliency point of view, as moving parts are the ones that tend to break down, need constant repair, and cause a lot of downtime. Finally, it's a direct process. If you compare this to a traditional way of converting natural gas to energy, you have to combust it, which produces heat. That heat in turn moves some sort of mechanical object, typically a turbine, that excites a magnetic field, and you have 3 or 4 energy conversion steps between the chemical energy and the electric energy. Ours is direct and allows us to be a lot more responsive and a lot more efficient. Now in the bottom of the screen, I show how we take that cell and build it up into those energy farms and the hundreds of megawatts that these AI factories need. So it's the same unit copy pasted over and over again to the stack. We take about 60 to 70 stacks to produce a power module, about 5 power modules with some ancillary equipment as an energy server, and that's that Lego block that scales up and down. Each power module operates independently. So if there is any downtime for whatever reason, the rest of the energy server continues to operate, the rest of the energy farm continues to operate. This leads to incredibly high uptime and gives us a lot of flexibility in meeting our customers' resiliency needs. With that, let's talk a little bit about what I'm hearing from the data center space. More and more, because of the time to power need and the sense of urgency in the industry, these customers are switching to on-site power. The grid's just not able to deliver them fast enough. And they're looking at other technologies as well. Specifically on the top, I've got a gas turbine there on the left, then a gas engine, and then a fuel cell. What I hear from you in the industry that's important is the reliability, the cost, the time to power, the ability to load follow. More and more as data center loads move from CPUs to GPUs, the load dynamics are variable and require fast response from your energy technology. Power density, right? Any space in a data center that's not used to generate revenue via the GPUs or the data center itself is space wasted, and they want the energy assets as they go on site to be extremely power dense. And of course, sustainability. A lot of these companies have made commitments that are important, and they're all striving to do this and achieve their business goals while doing it in a clean and responsible way. So let's talk a little bit about the reliability. Bloom itself is on our 6th generation of technology. It's something we've focused on a lot and constantly iterated. You can see at the bottom some statistics that we're really proud of. If you look at the total lifetime hours of individual units, we're in the millions. This is a significant amount of learning and a significant experience, and the system's been constantly improved, and we're a learning organization always making our systems better. For installations that are microgrids, that means they're able to operate an island and when the grid's down, we have the availability statistic down there. And that's something we measure ourselves on constantly and are always making sure that we deliver the most value to our customer through that. Now, for the next set of slides, I'm going to use that to kind of show you how that links to the economics. So a couple of key concepts I'm going to introduce here. First of all, let's imagine that there's a 100 megawatt AI factory, all right? When I talk to you in the industry and I ask what sort of availability you're looking for from your power generation assets, I often get the answer of 3 nines. Why? Because that's roughly the availability of the grid, and you're already investing in the UPS and diesel, so you don't need your power generation asset to be better than the grid. You just want it as good as what you had. Now, hit to that 3 nines, there's a couple of factors that really go into the math that determines that. It's what is the block size of the unit that's being built, as well as how available it is. So if you think of a gas turbine, right, a large open cycle turbine that's in the tens of megawatts, let's say 50 megawatts, the availability on that is pretty good. It's about 95%. But because there's that 5% where it's not available, you have to build that third unit in order to make sure that you're hitting that 99.9% availability for your 100 megawatt load. So that's about a 50% overbuild is what we say in the industry. Now, if we take that to smaller gas engines, which are slightly less available, but still pretty available at 93%, because the individual building block is smaller and the blast radius when something goes wrong is smaller, you need to overbuild less. So what we see in the gas engines is it's somewhere between 30 to 50% is the overbuild that they need in order to hit that 3.9 availability for that 100 megawatt AI factory. Now, fuel cells themselves, as we saw, are about 325 kilowatts of each building block. The individual units availability is about 99.7%, significantly higher than those other technologies. Because of the smaller power block size as well as the higher availability, we need much less overbuild to hit that 3 nines number. In fact, our number is about 9 to 10%. This becomes extremely significant. Think of the capex you're saving, right? That too, it's stranded capex on units that you hope to never use. Additionally, it's the space, the complexity, Downstream of the asset, that means less transformers, less copper, less infrastructure that has to be built on the site just because of of these statistics here. Let's translate that a little bit into CapEx, into the economics. So first, before I jump in, this is a theoretical data center. Every site's vastly different. Install conditions, time of power, etc., all go into determining the economics. But one view of it is presented here, where you can see the fuel cell. It's about equal price to the reciprocating engine, and it's a touch above an Opal Cycles turbine on a dollar per kilowatt basis. But in terms of total capex, because of the less overbuild required to hit that 3.9 requirement, there's significant capex savings when you're trying to build that Bloom project. In fact, it's about $80 million in the case I'm presenting right here. Now, for OpEx, if we imagine a $5 MMBTU gas, which is the rough cost of gas somewhere here in the US, you can see our efficiency is pretty significantly higher. And that means there's less gas consumed per unit of energy. That means by to deliver that same power for that 100 megawatt AI factory, it's about $12 to $15 million in savings just from the gas alone. Take that on a 5-year view, and you can see we're saving about 20 to 25% overall between the capex and the as well as the gas cost. I've got the service cost numbers here as well, and there's some savings there as well. So all of these factors add in, and this becomes really compelling for our data center customers. Let's talk a little bit about load following. So more and more we're seeing from our data center customers that as they run these training algorithms and here I've got a large language modules example that's running on the Llama on actual NVIDIA chips, you can see there's huge fluctuations in the power that they need, right? These algorithms are constantly checking themselves, writing things to memory, and that requires a change in the amount of power that they need. Because our fuel cells are that direct energy conversion and they don't have those intermittent energy conversion steps of going to the thermal energy and then to the mechanical energy, so on and so forth, we're able to respond much faster and more directly. And you can see here, the fuel cell system is able to keep up with that server AI load. We talked a little bit about the power density, and I just wanted to put some numbers out there for you. So our customers have a number of ways of installing our systems. If it's just, plenty of land available and you have the space, we'll just do a simple one level installation, and that's about 30 megawatts an acre. But more and more, we're seeing customers really get sensitive about the space they have, especially customers in urban, dense areas, such as where I live in the Bay Area. New York is another example. We have a lot of installations in Korea. Seoul energy space is an extreme premium over there. And we go into these stacking solutions. All the way up to 4 levels, we can reach 100 megawatts an acre. And this is extremely power dense and pretty significant for our customers. On the sustainability side, we talked about that less CO2. Because we're more efficient and we're consuming about 35% less gas, that means there's 35% less CO2 coming out. Near zero NOx, near zero NOx, near zero particulate matter. Water. Water is becoming an incredibly important resource, and power generation typically is an extremely thirsty endeavor. Our process, once it's up and running and we're in steady state operations, requires zero water. We are water neutral. That's significant savings, and that becomes really important, especially in jurisdictions like California and Arizona, where water is at a premium. Finally, noise. These systems are extremely quiet. The statistic is where we produce about 65 decibel at 10 feet. To put that in perspective, our headquarters, where I'm sitting here today, is powered by a fuel cell. I often host customers and give them tours and show off those systems. You can have a conversation easily in front of our system. This is really unique in the power generation space. In fact, when you're standing there in front of our systems, the freeway that's about half a mile away is significantly louder than the system itself. This allows customers to install it in places near their cafeterias, around their facility where their employees are, and gives you a lot more flexibility in how you use these assets. Finally, the time to power. So this was highlighted at the beginning of the webinar as the most important factor. And we're proud to say that we're able to deliver power to our customers within 90 days. Now, there's really a couple of ideas that go behind this. First of all, we have significant manufacturing capacity. We publicly stated that we have about a gigawatt per year of capacity today, and we're going to expand that to 2 gigawatts by the end of next year. This comes from 2 facilities. We have a facility here in Fremont, California, and we do final assembly in Delaware. Not only is it the factory itself, but we have a robust supply chain where we're multiple sourced on all key components that we've invested in heavily over the last few years that goes on behind that. The second part is the permitting, right? So we can deliver the fuel cells as fast as possible, but you also need a permit to operate. Now, this varies, of course, jurisdiction to jurisdiction, but because of the sustainability profile, because of the low noise, very often we're looked upon favorably by permitting agencies. In fact, even California, which has some of the strictest air permitting boards in the world, there are jurisdictions where we're exempt from the air permitting process, allowing us to be extremely quick in the way we deliver power relative to other solutions. Finally, and I think most significantly, this is a technology that's future ready. More and more, we're seeing customers try and realize more value from these systems. So, first and foremost is heat capture. A natural question when I showed you the efficiencies 50 to 54% is where does the remaining 50 to 45% go? And the answer is most of it goes into heat. More and more, we're seeing customers capture that heat and use it in a meaningful way to either reduce their costs or generate additional value. We've seen customers use it to heat up water and contribute to the district heating, especially in places like Europe and Korea, etc. We've seen customers convert it to steam and use it in industrial processes. More and more, and the one that I'm most excited about, is we've seen customers use an absorption chiller and convert it to cooling. This becomes really important in the data center space because cooling is an important energy consumption in the data center itself too. More and more, as GPUs become more power dense and rack densities increase, the amount of heat that's produced per unit area in the data center is going up exponentially, and cooling is going to become more and more important. Another value stream is carbon capture. This is something we're working very hard on and working very carefully with. If you look at our chemical reaction, because it's non-combustion, even though we have less CO2, that CO2 is emitted at a much higher concentration compared to combustion technologies. This means to capture it, to either utilize it or sequester it and do something meaningful with it, it requires a lot less capex and a lot less energy. In fact, we publicly announced a partnership with Chart, and we're working on a project that's going to demonstrate this technology and many more things to come around that. DC power. Fuel cells are natively producing direct current power. Today, a data center takes the AC power from the grid, converts it to DC, converts it back to AC, and then finally converts it back to DC at the rack level. That's a lot of unnecessary back and forth and conversions. More and more, we're hearing data centers look towards adopting standards around 800-volt DC architecture, and that is natively where we produce our power. It's an application we're very excited from and will lead to significant savings of CapEx as well as OpEx from the efficiency. If you think about it, one of the limiting factors as we think about how the data center boom is happening is the copper and the transformers. The ability to take power DC reduces your need and dependencies on that and allows you to get so much more. Finally, as and when other fuels become commercially viable and available, we are a fuel flexible technology. We can run on hydrogen today. We can run on blends thereof of hydrogen as well as natural gas. We can run on biogas and extremely flexible, allowing our customers to adopt as time goes on. This becomes really important to our customers because they need the power today, right? There's the sense of urgency, their businesses need it, but they know over time that they are going to want to do the right thing and be sustainable. This gives them a couple of options on the technology to allow it to realize those goals and gives them the confidence to invest in us over the long term. With that, I am going to suggest that you scan this QR code, and there'll be a link in the chat as well, and download this write-up that we have. This is a great report that goes into a lot more detail in what I talked about today.